So I wanna connect up a little bit of what we've been talking about with respect to OSLF to some implementation stuff, so people have a sense of what we're talking about. So what I'd like is to quickly point folks to Kiama. So Tomislav and Will, are you familiar with Kiama?
I'm familiar because you wrote your conversion between pi and the rho, but that's all.
Okay, so essentially what Kiama does is it allows you to do, you can specify rewrite systems in a syntax that's similar to the way we do it in the academic style. So when we're presenting papers, we use the some version of SOS, the structured operational semantics. And so Kiama basically provides a framework for that. So the idea is that your syntax is going to be case classes. So we'll talk about that in a second. And then your rewrite rules are going to be of the form of a particular form. So let's imagine. So they don't have it here, but let's imagine what the case classes for lambda would be, right? So the case classes for lambda, you'd have a trait, let's call it exp for expression, and then you'd have a trait for variable a case class for variable mentions, and we might consider that that's parametric in whatever the type of variable is or the type of identifiers is. Does that make sense? Can you kind of picture that in your mind?
Yes, yes.
And then we would have a case class for abstraction, and so that would have two fields in it, right? One of which is for the arguments, and one of which is for the body of the abstraction. And then we would have a case class for application, which would have, again, two slots in it, one for the operator or the function, and the other for the arguments.
Yeah.
Okay, so then in Kiama 2.0, the beta reduction would look like this. So you declare a rule, it's parameterized in our trait expressions, and whenever you come across a term of the form application, if the first part of the application, the operator part or the function part, is a lambda term, right? So an abstraction, where we have the variable x is the formal argument to the abstraction, and t is the body, and let's see, what is E1 in this particular? Oh, probably the environment. No. XT. I don't know why he's got that should only have two expressions. I have to go look and see why he's encoding abstractions like that. There should only be two here in the usual encoding. So there's an extra argument here. So T is the funny one. We can see that because of the substitution. So I have to go figure out what T is in this rule. But anyway, so ignoring T for the moment. So we have a lambda x over E1. And that abstraction is applied to E2, right? So that's the application. Then we do a substitute of E2 for x in E1. Does that make sense?
Yes, yes.
So this is exactly like, yes, we would write it in the paper, right? And you can imagine what a com rule would look like here.
Yeah.
Right? The com rule for rho. So this would be a par. This would be a for comprehension. And then you really would need three arguments, right? Because you need the the channel you're communicating over, the abstraction where you're going to receive the value, and then the body of the forecomprehension. And then this one, instead of just being an E2, it would be an output. Right? So if this is 4, this would be an output. The channels would have to match over what you're sending, and then you'd have a Q, and Q would be in the place of E2. At Q would be in the place of E2 when you do the substitution, right?
Yeah.
So that's so this is the nice thing is that this format is very, very close to the way we would do the way we write it in the paper. So now, go ahead.
I mean, it seems that this rule function accepts partial function. So basically, it must be in this format. If it's not, it's basically not defined.
That's correct. That's right.
That's nice.
You won't apply it. Yeah, that's correct. Okay, so now let's take a look here. These would be what in Scala?
Case classes.
Yes, but even more specifically, since this is a 1, what would it be? Not a case class, but a case.
Oh, case object, because they're
exactly right.
Constants. Yeah. Mm-hmm.
Yeah, exactly. And then the K would be your case class, and then the row would be your Kiama rule.
Mm-hmm.
Does that make sense?
Yes. Yes.
Okay. Very good.
Mm-hmm. Basically, this APP is like specific for lambda calculus, but we can define K, which is like completely abstract for any like any application or that we have, any rewrite, right?
That's correct. So now,
mm-hmm.
now remember, this is being supplied to us. So what that means is over here, someone is handing us a Kiama spec for their language.
Oh, yeah.
Okay, so we get Kiama source, right? And then we're going to produce something new, right? And the something new is the OSLF types, right? And the inference rules. Okay, so that's a way to think about the implementation. So this is our input, and now the first thing we're going to do is we're going to produce a new version, a new Kiama output, right? So these all remain the same. This remains the same. Now we're going to add a new case class, which is the R case class, right? And it has 1 slot in it, which is this T. Does that make sense?
Yes, yes.
And then the same here. We're going to add a new case class. How many slots does it have?
We need 2 slots.
Exactly, the same here.
Yeah.
Yeah.
Mm-hmm.
And then we're going to change. So we're going to this rewrite rule is going to be similar to this one, except that the source of it, in other words, the thing on the left-hand side here, is going to insist that it's going to be R of K.
Mm-hmm.
Does that make sense? Right?
Yes.
Okay, excellent. Now we're cooking with gas.
Mm-hmm.
So this is how the implementation could proceed in terms of Kiama.
And I'm thinking we don't need some kind of inspection of Kiama, some kind of Kiama types, right? We are just working with normal Scala case classes. So we are basically, someone is giving us one specification in Scala case classes, and we are generating another set of case classes.
That is correct. That is correct for the syntax.
Mm-hmm.
But they're also giving us Kiama rules. And so then we would have to we'd have to take that rule and produce a new Kiama rule. Does that make sense?
And yes, and is there some kind of way of inspection of Kiama rules?
So what we have to do is to go under the covers and figure out what this rule expression is, and then use Scala reflection on that.
Okay, understood.
Yeah, so you can use Scala reflection to implement the resource theory, right? Because this thing is going to have to know about T, and these two things are going to have to know about T.
Yeah.
Cool.
Okay.
All right. So then all of these are so here these are also going to be you know, how do I say this? We're going to make the data types or the OSLF types. We're going to make those types also be reified as Scala classes, right? But they're one level up. It would be nice if we could just hack directly into the Scala type system, and we might be able to do that with reflection. But you know, the simplest thing to do, you know, rather than trying to be clever, right? So for each of these case objects, we have new case objects, but these represent the type level as opposed to the term level. Does that make sense? So everywhere where you have an underbar, you know, you're having you're making a type object, a type kind of thing, right? So all of these come directly from the input we were handed. And then this is a type constructor, right? So given a type, it'll give you a new type. And so given like these case gadgets that came to us, you know, at the type level, inferred from the case classes at the term level. So this type tau, in other words, this is a Scala gadget that is parametric in a tau thing. Does that make sense?
Okay. Yes.
Okay, so this is a type constructor, parametric in that. And then these are also, you know, these are fixed points, right? So this is going to be a recursive type. So we'll do the gamma type constructor over top of these extensions, and likewise for the arrow in the context. Does that make sense?
Yes, I think it is. You mentioned we will infer from the term constructors. We will infer types.
Exactly. Right. Because go ahead.
Yeah, I'm just thinking. You said better at first. Better to not go and like define our types as a Scala types, but maybe to work on the value level in the Scala.
Yes.
In Scala code and define in that level types. So that will not be the real Scala types, right?
Well, I mean, so just to be super clear, where we have a case object C, right? At the term level, we're going to have case object C. Yes. Okay. So here we're going to have case object C type, because the underbar says it's a type rather than a term. So the Scala declaration will be case object C type. And likewise, there'll be a Scala declaration case class K type. So when you make an instance of that case class, it's going to be a Scala value, but what it represents is a type relative to these terms.
Yeah. So it's on a value level in Scala, but represents types.
Exactly. That is exactly it.
Okay.
Cool. So then let's look at some simple inference rules. So the axiom scheme, instead of, so this is not quite right. Instead of tau, what this will have to be is, again, parametric. So we'll make a notion of a rule, and we can do this with Kiama, right? That's one way to do it, or we can just have our own notion of type inference rules. Either one, it depends on some convenience aspects of Kiama, which I haven't figured out yet. I haven't studied Kiama deeply enough to know whether we can overload its semantics that way. But let's imagine that we have what are called type inference rules. Okay, so then a rule has got a bunch of hypotheses and a conclusion. So in that sense, these rules are like functions, a bunch of arguments and an output. Does that make sense?
Yes, yes. I just wanted to ask you that.
Yes. Yeah. Okay, good. So then the next piece of the puzzle is what are the types of the arguments and the output for one of these type inference rules. So the types are judgments. So a judgment is one of these kinds of things, or one of these kinds of things. And so we can, in general, we can, yeah. So let's just look at this one. So a judgment has two parts. There's stuff on the left and stuff on the right. In the intuitionistic case, it's again like a function. There's only one thing on the right and there's a list of things on the left. Does that make sense?
Yes.
Okay. And the stuff on the on either side are typing assertions. So a typing assertion is going to be something like X is of a given type, or T is of a given type, like here. So,
is this basically means that we at least we need this kind of things on the left, so we can conclude on the right.
That's exactly right. So assuming this, we can conclude that.
And we can have more, but we are searching only like what we need.
Exactly. So now you would have a Scala. Let's just stick with case classes for now, rather than try to do fancy factoring. Right. So you have a Scala case class for type assignment or type assertion. You have a Scala case class for a judgment. And then you have a Scala case class for an inference rule. And yeah. Okay. And then the thing about the rules is the one function you want is check. So you check a type assertion. Right. So given a type assertion, you do check, and then check takes the base of the rules, right? This knowledge base or database of rules, and how does it work? So it's going to try to find a rule in here, in this collection of rules that we have coded up, that where you get a match between the type assertion that was supplied and the conclusion. So by match, I mean unification. So we can unify the term part with the term part of the type assignment, and the type part with the type part of the type assertion. Once you have that, then you want to go backwards. So you'll run the rule backwards and say, well, in order to show this, I'm going to have to show this, and I'm going to have to show that. And notice that when we're in the simple case where we're just doing a check of a type assertion, the stuff on the left is empty. So we begin with empty. Does that make sense?
Yes, yes.
Okay, that's it. That's the whole, that is the whole basis for what we're doing. Now, if you can build a tree, if you run it backwards like that, and you can build a tree so that you ground out in axiom, then you know that your term is of the given type.
And and we will have type declarations. So, for example, when we create some term, we can specify the type. In that case, and this is like a already defined types, right? User is telling us this is the type.
The user says, "Here's my program, and here's the type that I think it is." And it's just like a user of Scala, they write down some programs, they write down types, right? And then the Scala compiler does the check.
And we have both. We are doing the checking, but also we are doing the inference in some cases, right?
Well, here we haven't talked about type inference. We've just talked about type checking.
Okay.
No inference yet. And in fact, if your system, if your rewrite rules here, if this thing is not confluent, as it isn't confluent for pi and it isn't confluent for rho, then inference is becomes impossible for formulae that include lollipop.
I wanted to ask why is this for? Because we have multiple. Is this completely impossible, or we have multiple branches to infer, and then we can have multiple types?
You could do that. You can't get a principal type, but you could get multiple types.
So this is something that maybe IDE can offer to user. And
yeah, it will work like Prolog. Well, here's the first solution. Here's the next solution. Here's the next solution.
Okay, nice.
Something like that. All right, that's all I wanted to talk about today. Nice little bite-sized chunk. How you would go about implementing this part of OSLF. Now, obviously, you could run this as a brute force if you were going to now wire this up to GitHub or wire this up to the blockchain in terms of the smart contracts that are stored there, right? So then you could, someone could type in a function find. And now instead of producing a term and a type, they just give a type. They say find type, right? So let's say we're going to a GitHub repository. And let's say they say find type, but only from the following repos. I'm not interested in all the repos on GitHub, and they give you a list of repos. And just for simplicity of our discussion, let's say that the list contains exactly one repo. This is without loss of generality. So the brute force approach is you then download all of the code, all of the programs, and these would be, independent programs, not subterms of given terms, but standalone terms, right? So you download all the programs, and then you would do you'd call check using, the first program and the type the user supplied. And if that checked, you throw it in the results you're going to return to the user. If it doesn't check, then you throw it away and you go to the next one. Does that make sense?
Yes.
So that's how you do search using types against GitHub.
Yeah, this makes sense. And in the same way, we can, when we are searching the types, we can also create some kind of indexes and to speed up search and offer more.
That's exactly right. That's exactly right. Yes. Yeah. Yeah. I'm just giving you the brute force algorithm, but there are clever ways to not have to do the brute force.
Yeah, this is very nice.
Cool. Cool. All right. That's it. That's it. I'm actually going to take this 30 minutes and use it to take care of some stuff. It is 4:30 in the morning where I am. Okay.
Thanks. I'm glad that you explained this because I was wondering about implementation and more concrete stuff. So
yeah,
yes.
This is like finally we see some meat and potatoes here.
Well, I mean, the interesting point is that if you learn the mapping from the math to the code, the math is faster.
How many years will that take me?
Well, I just gave you the mapping, so you can,
Yeah.
and it's recorded, and so you can listen to it a few times. And, all right, thanks to all, and I'll see you at stand up in a little bit.
Okay.
Thank you.
All right. Thank you.
Bye bye.